Hey guys, welcome to Magnetism Part 12. In this video, we're going to be taking a look at solenoids and toroids. Now we're going to first look at them qualitatively. So we're going to take a look at how the magnetic fields align and superposition to make them into electromagnets and other electrical components. And then in the following video, we'll look at them from the perspective of using the Ampere's law or the Biot-Savart law to figure out how we would calculate the strength of the magnetic field around each. So without further ado, let's get into it. Now, solenoids and toroids have a variety of applications, but we're going to start by looking at theoretically how they're structured and how their mechanisms work. Once we know this, we'll be able to apply them to many different situations. But to whet your appetite a little bit, let's just think about a few of the things where solenoids are used. They form the basis of things like transformers, inductors, or things like the motor or a generator. They're also used in headphones and speakers, and pretty much many electrical components include them in some way or another. So here's a picture of a basic solenoid. It's a coil of wire wrapped around some sort of central cylinder. Now the cylinder can be removed and I can have open space in between, or I can include a core of some kind, iron or something else, or a magnetic core, in the sense of when I have an inductor or if I have a transformer. But we're going to take a look at this solenoid first that has just open space in between the middle of the coil. Now, a solenoid is usually or will be connected to a power supply. So we would have current flowing through the solenoid, looping around and around this wire. So in order to better visualize the direction of the current at any given time, it's easiest to create a cross-section of the solenoid. So if you imagine the solenoid as a hot dog bun, and I slice it down the center to open it up, and I'm only looking at one half of the bun, if I did this with a solenoid, it might look like something like this. So each of the little circles that you see here in this image represents a cross-section of the wire. Now let's think about the direction of this current. Well, based on this configuration, if I have the current flowing into this end of the solenoid, that would mean that the current is flowing into the page or into the screen at the top and flowing out of the screen at the bottom. Now what ends up being very interesting is that if it's cut exactly in a cross-section like this, all of the lines at the top will be X's or be into the screen, and all of the lines or the wire at the bottom would be coming out of the screen. Now remember, this is one continuous wire. They look individual here because of the way that we've cut the wire in order for us to be able to see this. Now we're going to revisit the right-hand rule number 2, or the corkscrew version of the right-hand rule, where our thumb represents the current and our fingers represent the magnetic field. So let's take a look at one of the wires on the top. Now we see that the current's directed into the screen, so our thumb on our right hand should point into the screen, leaving our fingers to wrap clockwise around one particular piece of the wire. Now because all of the pieces on the bottom have current directed into the screen, all of them will also have a magnetic field that is clockwise around the solenoid. Now that's the opposite on the top, whereas if I point my thumb out of the screen in the direction of the current at any given location in that wire, I would see that the magnetic field points counterclockwise. Now, just as we saw with wires that overlap and create some sort of net magnetic field at a location, the same thing will happen here through the principle of superposition, also known as overlapping magnetic fields. So like any wave where the peaks or the troughs of the wave overlap, we have constructive interference or destructive interference. So we're going to think of it in that way. Wherever these waves or directions of the magnetic field from the vector sense overlap in the same direction, they will create a stronger magnetic field. And wherever they overlap in the opposite direction, or the vectors point in opposite directions, they will cancel out or create a weaker magnetic field. So I'm going to spread the solenoid out so I have a little bit of space, and I'm going to draw a circular magnetic field around each piece of the wire that we see here. So let's just focus on one region of the wire. Let's say a region on the top that has an X representing the current going into the screen. My fingers, or the circle that represents the magnetic field, wraps clockwise around, and we're going to focus on 4 distinct regions around that piece of wire. A tangent line, or tangent magnetic field, at the instant right above the wire, below that piece of wire, to the right of it and to the left of it. So let's analyze the tangent magnetic field at the top of that wire. So we see that it points to the right, and if we did so for each and every one of the pieces of wire, we'd see they'd all add up pointing to the right. Now, for the pieces of magnetic field, or the tangent magnetic field, to the left of each of those pieces of wire, we see them pointing up. And the tangent on the right of each of those magnetic fields around each piece of wire, we see those pointing straight down. So if we extrapolate this to each segment of wire, we see that in between each of the wires, we have an upward pointing and a downward pointing magnetic field, which means that the magnetic field between the wire coils of the solenoid end up actually canceling out. Now, through the center of the solenoid is where we want to pay most attention. If we take a look at how we have the structure right now, the tangent magnetic field at the bottom of each of the magnetic fields wrapped around each piece of the coil all point to the left at exactly the tangent part in the center. This means that they all superposition in the same direction, and the magnetic field is strengthened. Now, let's take a look at the bottom, but I want you to try to do it first to see if you're understanding what we've been talking about. So pause the video and try to draw what we drew for the top section, but for the bottom, where the current is directed out of the screen. We see in between each of the coils that the magnetic field pointing up or down from each subsequent piece of the solenoid cancels out, thereby canceling out the magnetic field. We see the same scenario occur on the outside, where all the field lines point in the same direction, and on the inside we see that the magnetic field tangent to each of the little wires points to the left as well, just like it did on the top, strengthening the magnetic field on the inside by a whole lot more. So by the end of this analysis, we see that all of the magnetic field lines are pointing in one direction on the inside. This makes for a very strong magnetic field on the inside. Now you can imagine that adding more and more coils, or more and more loops of wire around the center, will create an even stronger magnetic field, where we just keep overlapping the magnetic field more and more and more. Now, if you've ever tried to make a solenoid on your own through an experiment, or if you try to make your own little electromagnet, as I showed in a previous video, you know that the electromagnet is only as good as your carefulness about wrapping the wire. Because you can tell that if the wire is not all directed in the same way, the superpositioning will not be as effective, and you will have a slightly distorted magnetic field. Now, we have one more right-hand rule to add so far, and that one is right-hand rule solenoid, as it's sometimes described. The numbering is different from book to book, but we're going to go ahead and call this right-hand rule number 3. Now, right-hand rule number 3 looks very much the same as right-hand rule number 2 because we use our thumb and our fingers. However, now we're going to switch the meaning of the fingers to the thumb. So before, our thumb represented the current direction and our fingers represented the direction of the magnetic field coiling around a wire. Now we're going to say that each finger represents one of the wires, or 4 of the wires, in the solenoid, the direction of their current, and our thumb will point in the direction of the north end of the bar magnet that we've just created. Now, it's not really a bar magnet, but if we were to superimpose a bar magnet on the inside of the solenoid, we would see that our thumb points in the direction of the north end of the imaginary bar magnet. So let's say, for instance, that in our image here, we have current pointing into the page or into the screen, and so we have each finger as a separate wire going into the screen, leaving our thumb pointing to the right. We'd see that it still follows the bottom part of our solenoid where our fingers would be pointing out, or the current's pointing out of the screen, leaving our thumb to the left. Now, this actually turns out to be a very important mechanism, because we know that if we switch the direction of the current, then I would have switched the poles of this electromagnet. So I think this is one of the coolest things in all of physics, really, that you can take a wire, run current through it, and have created essentially a little bar magnet or an electromagnet. This thing can be altered by the number of turns, the strength of the current, and many different things that we'll look at mathematically in the next video. So finally, let's take a look at the toroid. Now, a toroid is basically something that looks just like this. Now, this is used in many different applications as well, and forms a very similar foundation to the solenoid. It basically is a solenoid in a different shape, a donut shape, if you will. So if I take the solenoid, focusing purely on the magnetic field on the inside of the solenoid, and I imagine it being almost like a rolled piece of dough. If I then wrap the dough around to join the edges to create almost a donut shape, I would see that the magnetic field actually bends around in the center, and so I create this sort of loop of magnetic field. Now, if you want to use the second right-hand rule again to figure out the directions, you would see that on the inside I have every single little tangent piece of magnetic field to each of the wires pieces on the outside versus the inside, all pointing in the same direction within the inside of the loop. So if we assess the direction of the magnetic field by that right-hand rule, we see that we've effectively created sort of a donut of magnetic field that's pretty strong. So in the next video, we'll take a look at the quantitative aspect of the toroid and the solenoid. We'll take a look at how current strength, number of loops, and even the dimensions of the solenoid can affect the magnetic field strength. Then we'll take a look at how they can be harnessed in inductors and inductor circuits. See you soon.